I want to summarize this lecture. And at the beginning of this lecture, I talk about some oscillating source in space. And this oscillating source could be a current source or a charge source. And if you have an oscillating source in space, then at some time later, you could detect some signal far away from the source, and there's a time delay associated with it. And from this observation, we can say that there's a wave propagating in space. And I talk about wave equations for electric field and magnetic field because the electric field and magnetic field are the physical parameters propagating as a wave in space. And there's a finite speed associated with it. Therefore, at some time later, you can detect electromagnetic signal from this oscillating source. And the finite speed is calculated to be U equal to 1 over square root of mu epsilon. And mu, again, is the permeability of the medium, and epsilon is the permittivity of the medium. And even though the medium could be vacuum, there's a finite value of mu and epsilon. And then I introduced you a plane wave as a guessing solution to the Helmholtz equation. And a plane wave will have this form. So if you just set the phase to be a constant, then you're going to see that the position will fall on a plane. And that's why we call this expression as a solution for a plane wave, because the wavefront is a plane based on this construction. And this kxx, kyy, kzz can be written into the dot product of two vectors. And if you set this to be a constant, this means that the positions, all the coordinates in space under this condition will fall on the plane, a plane, because the r dot an has to be a constant. And then the real solution can be constructed from a phasor solution. Just pick up a phasor solution and multiply this with the exponential j omega t and take real part of it. You will end up having this expression. So this is the real solution for a plane wave. And in front of this cosine, there's a vector, amplitude vector in front of it. And the first point I mentioned in this lecture is that I do some geometric construction for the k vector. So given the k vector in space, then there will be three angles that can be defined to be the angles between k and x-axis, y-axis and z-axis. Let's call those three angles to be alpha, beta, gamma. Then if you project, for example, this k onto x-axis, then you can calculate kx equal to k cosine alpha. So the k vectors now are defined by those direction cosines given by this expression. And with this construction, then it's also easy to calculate the phase velocity along three different directions, x, y, z. So the now kx, ky, kz are well defined to be k multiplying with cosine alpha or cosine beta or cosine gamma. So the phase velocities along x, y, z direction will be given by this expression. For example, if you want to know the phase velocity along y direction, then the value is going to be the phase velocity along this an direction divided by cosine beta. And this cosine value in general is less than 1. So the phase velocities along different directions, along directions other than the an direction, is going to be larger than the phase velocity along an direction. And also we can also look into the wavelengths along different directions. And the wavelengths along x, y, z directions is given by this expression. And for example, if we want to look into or calculate the wavelengths along x direction, then the value is going to be equal to the wavelength along AN direction divided by cosine alpha. And again, this cosine alpha is less than 1. So in general, if you calculate the wavelength along, say, x direction or y direction, the wavelength is going to be longer than this wavelength along k direction, along the AN direction. And then we introduce the intrinsic wave impedance. That is a ratio between electric field and magnetic field. In vacuum, this value is 377 ohm. And we also deduce the relationship between magnetic field and electric field for wave. For example, if you know the solution for electric field right here, then you can calculate the value of the magnetic field through this expression. But this expression tells you more on the directional relationship between the H field, E field, and K vector. From the Ampere's law, you can also deduce this expression, and turn out that if you know the magnetic field, you can also calculate the electric field from this expression. In the end of this lecture, I conclude this lecture with the directional relationship among the electric field, magnetic field, and also the K vector. And we derived these two expressions. And these two expressions will tell you the electric field and magnetic field and the K vector are perpendicular to each other. And so in this three-dimensional figure, the directions of E, H, and K have to be consistent with the right-hand rule in these two equations. And because the electric field and magnetic field are perpendicular to the propagation direction of the wavefront, so we call this wave a transverse electromagnetic wave. And a short notation for this name is the TEM wave. And this TEM wave is the simplest plane wave for analysis. You should remember it. Thank you for your attention.